spoked wheel. Do you guys remember that? Before we do that, or go back to that, and just clearly, let me make sure I've pointed it out. You have homework assignments, 2 of them assigned. They're broken up into small groups on purpose. Start the first one. Tonight, go home, put this to use. Do the first problem on the first assignment. It's very much in line with what we're going to be doing today. I found that it would be best based on my, based on what happened in the last class period, if we spend a minute just in reminder of what you had to do first semester. So in first semester, you might have had a problem like this. One in which we had a mass hung on either side of a light pulley. I would have used that phrase, light pulley. And you might have been asked to figure out, well, what is the acceleration of the system, assuming the pulley has no mass? So hang the pulley from the ceiling. Let's say that this side is mass m and this side is mass 2m. We've done this problem a ton of times. My expectation is that I shouldn't have to wait very long for you to have this answer. But my experience is some of you, well, this was more than a week ago, so you have forgotten how to do all of this. So show me I'm wrong and point to the answer for the acceleration of the system in 60 seconds. So I'm going to set this direction to be positive on this side and this direction to be positive on this side, and assume that the pulley is going to spin in that direction. The pulley is massless, and because of that, I can focus on the masses themselves. I assume that the box on the left, for every meter it moves downwards, the box on the right moves a meter upwards. Do you remember all these kinds of questions I told you guys to think about in doing them? And you should. Now, the box on the right is experiencing 2 forces, an upward force of tension and a downward force of weight, while the box on the left side is experiencing the same upward force of tension, but a heavier force of weight because it's twice the mass. The net force on the left will be equal to 2ma because the inertia of this box is 2m, while the box on the right will have an acceleration related to ma. Being consistent with my direction, I should get 2mg minus t equals 2ma. And on the right, I get just t minus mg equals ma. I have 2 equations and 2 unknowns where I can eliminate the tension between them and be left with something that has just acceleration in it. On the left side, I'll get 2mg minus mg equals 3ma. I pause here to remind us that what you should always get in working one of these problems is something that mimics Newton's second law. Net force equals total inertia times acceleration. Total inertia of the system is 3m. Either way, solving for A, I get 1/3 g. It was about a minute. Minute and 12 seconds because I talked out loud the whole time. Okay, so we've set the bar. I am disappointed. I asked you guys yesterday to take a object and find the composite moment of inertia. I don't want to walk around the room to see who didn't do it because then I will just be more frustrated. So I'm already frustrated with the people in one of my other classes for not doing the work that I had asked them to do. I don't want to actually add you guys to that list because some of you are in that other class, and that will make me sad to know that you didn't do any of the things I asked. But I do want to spend a moment because I did this not incorrectly, but I did make something clear when we did this in 6th period, and it caused a little bit of concern. This is the system I wanted you to find the moment of inertia of for homework. And I hope that you found that it was 5/3 mr squared. That's what you should have found. Now I'm seeing a few people like this, but I'm also seeing some faces that suggest they either found nothing or found something different. So let's remember that this had a mass of m, this bar had a mass of m, and this bar had a mass of m. The mass of the system is 3m. We good with that? Everybody understand what I just did? Each thing had the same mass. However, one of these was a disk. Its moment of inertia is mr squared. The other two are both bars spun around their center of mass, which is 1/12 ml squared. So 1/12 m2r squared. Right? The bars were length 2r, which makes 4r squared, or 1/3 mr squared. And there are two of them. So this is 2/3 mr squared. I'm going fast because you were supposed to do this for homework. Adding 2/3 to 1, you get a total moment of inertia of 5/3 mr squared. We good? Hope so, because we're just getting warmed up.
What if you did it in terms of L, and you made the R 1/2 L?
Then yours would be in terms of L, and it's not incorrect, but you're going to want it in terms of the radius. I guarantee it. So I would encourage you right now to leave in terms of the radius. On an actual AP question, you'll be able to, later because I need it, but let's come back to this. We're going to repeat the problem. But in today's version of the problem, our system is going to be rotated about its center and has something holding it in place so that it pivots about its middle. We're still going to hang a mass on both sides. So I have a mass on this side, and that mass is still going to be mg. We're simply repeating that part of the problem. So this one's mass m, and I have a force on this side. And it too is going to be the same as the last one. So its mass is 2m. Now, this problem is very similar to what we just did, with one very clear and obvious difference. The wheel has inertia. It will resist changes in motion. Therefore, I expect in the end of this problem for my system's acceleration to be affected by the wheel. Yes? Say it. Get it out. Let's work it out. 1/12 times mr squared. 2 squared is 4. That's this, right? That's what this is, which makes this 4/12. Is that it? Okay. All right. So I'm actually going to take all this away. We don't need any of this now. I left it up there long enough to make sure everybody who was working it out was able to get the answer on their own, and I feel confident that we're there. Now, first, let's consider there's a big difference in this problem. It may not seem like it, but there's a big difference. Let's step through this problem. There's still going to be an unbalanced force lifting this side up. So I'm going to make upwards positive on this side and downwards positive on this side. I still think it's going to rotate in the same direction. I just think it's going to rotate at a different acceleration. And I believe the wheel is going to accelerate this way. I'm going to make that direction the positive direction of acceleration. Now let's handle all the parts to this. Positive direction of acceleration means that the direction of acceleration of the wheel will be out of the board. If its pivot point is here, and I use the right-hand rule, the wheel is going to be accelerating this direction. That is a direction out of the board for its rotation. So I am stating clearly that out of the board is the positive rotational direction for the wheel. The symbol for that would be a circle with a dot in it, but I'm saying that that direction is positive. Everybody okay with that? Out of the board, positive. We need to be. Now, you may wish to set this problem up the same way as before, and you would not be all the way wrong doing so. The block on the right is experiencing an upward tension force. That has not changed. And it's experiencing a downward force of weight. That hasn't changed. The box on the left, similarly, is experiencing an upward force of tension and a downward force of weight. That hasn't changed. My original problem here, these are not the same tensions. This will be the tension I record on the left, and this is the tension I record on the right. And my belief, and it's a very strong belief in science, is that TR will be less than TL. Now, nothing else over here has changed. This is still 2mg minus TL equals 2ma. That's still true. And on this side, I'm still going to have TR minus mg equals ma. Ugh. That's still true. I just now can't set these two tensions equal to each other. Now go back to pulley to not worry about that, because you'll be told quite clearly to do everything in terms of one of the specific variables. Does that make sense? All right, I'm going to save that. So although these forces have to sum to be zero, and I don't know what you want to call this. You can call this a normal force from the mounting point. I don't care. There's got to be forces there. But the only way the pulley accelerates, meaning the only way the pulley has an angular acceleration, is if there's an unbalanced torque. This is Newton's second law for torques. Those will not be zero. Our pulley is going to accelerate. Now, it should be clear to you that if the pivot point is at the center, the weight doesn't apply a torque, and the normal force that's mounting the pulley there doesn't apply a torque. But these two tensions must apply a torque, because they act with a torque arm distance of r in both directions. Now, this is the important part, the part you really should listen to. The only way the system can accelerate is if these two torques are different. And if they have the same torque arm length, then one of these forces has to be less than the other. Has to be. In a system in which your pulley has mass, your tension is no longer the same on all the parts of the pulley. You will have to treat them as different. So there's tension on the left and tension on the right, and they will not be the same because our torques can't be the same. If they are, there's no acceleration and the wheel does not turn. Does everybody understand? I'm sorry, let me say it different. Did everybody write that down so that they can study it later? I'm indifferent to whether you understand that right now or not, because some of you won't. But you need to know that there can be no acceleration without an unbalanced torque. Having a massive pulley means that there's going to be a change in the tension as it goes around the pulley. The only way I'm going to solve this is if I can find a way to relate TL and TR. That's where torque comes in. We need to create a torque relationship. Now, just a reminder, torque is defined as R cross cross F, or in the circumstance of the magnitude, R times F times the sine of the angle. This became a thing in sixth period, so I don't want it to be a thing in this period. The angle is going to be 90 degrees for all pulleys. There's no way for the string to come off a pulley in any direction that isn't tangent to the pulley. I mean, if I try to change, if I try to pull the pulley with an angle that's different, you understand the string will just unwrap until it comes to a point on the pulley that is tangent. Does everybody understand what I'm saying? If not, I don't really care, but try it. Try to pull the string off a pulley and have it not come off at a tangent. There's just no way. But if it comes off at a tangent, then that means it will automatically be perpendicular to any radius. So when you use a pulley, the angle between the torque arm and the pulling force of tension is always going to be 90 degrees. So I see two tensions here, right? Therefore, I see two torques. I think there's going to be the torque on the left and the torque on the right. And because I want to be deliberate, I'm going to set up all the torques using as basic an idea as possible. I just put all those three things together so that we can kind of carefully work out each of those. Now, the normal force does not apply a torque because it's at the center. And the weight does not apply a torque because it's at the center. The pivot point is at the center. This is not a statics problem where we can choose the pivot point. Pulleys have a fixed pivot point and we use them. So we have to use the actual place in which the system pivots. Now, finding torque isn't hard. I'm pretty sure we would all agree that, starting with TL, the torque arm is going to be the radius of the pulley. And the force on this side is going to be TL, because it's the left tension, times the sine of 90 degrees, as explained a minute ago. Let's deal with direction, though. Right-hand rule for direction. I point my pointer finger in the direction of the torque arm first, and then roll my finger until my middle finger is in the direction of the force that acts at the end of that torque arm, which is downwards. My thumb points out of the board. So this tension is a positive torque and is trying to turn the wheel in the direction that we call positive. I'm not surprised. That's where the heavier one is. So that is our positive torque. Let's go to the left one. Torque arm on this side, still the radius of the pulley. Now, this will only be true. This doesn't have to be true. You can have systems in which these two tensions are different or have different radii. You can have a gear system in which one weight is hung on one side and that has a different radius than the other side. I give you one in one of your homework questions. If you don't know what I'm talking about, look it up. But also, if it's not circular, they can have different radii. There are plenty of things that spin that aren't circles. But a circular pulley does sure make the math nice. The right side is just tension on the right, still sine 90 degrees. And I could just put negative there, but I think it's appropriate that we practice the right-hand rule. So this is the direction of our torque arm on this side. Using my right hand, point outward, line up my finger with the force. My thumb points into the board. That's a negative torque. We said out of the board is positive, so into the board must be negative. So this is a negative torque. Now we're going to construct our torque equation. It is Newton's second law, but for torque. That's just adding these two things together and setting it equal to I alpha. So I will have RTL minus RTR equals 5/3 mr squared times alpha. I know I'm jumping a little ahead, but not much, reminding us that that moment of inertia is what we solved for earlier in the problem. All right. That's a lot. Of course. Sorry. We kind of had a pause, and now we're coming back to the problem. We have just finished going over the torque portion of the problem and produced a torque relationship from Newton's second law related to torque. I'm bringing all that up because this relationship has forces in it, but also has an angular acceleration in it. Now, in our prior problems, we attempted to eliminate variables to leave us with an answer for acceleration. In fact, let's bring in all the pieces that we have. I don't need the picture for this. Actually, I might. So let me leave the picture here. But we have two force equations now, right? We have 2mg minus TL equals 2ma. And we have TR minus mg equals ma. Just rewriting them here. In the past times we've done this, we could add these together, the tensions would cancel out, and we would be left with something that had just acceleration in it. But you understand that we don't have the capacity to do that in this instance because we have, first, these r's that are kind of plugging everything up. Now, in order for this system to accelerate, in order for us to solve this, we need to find a way to bring these things together. You have to ask an important question, and it determines whether you can go on or not. Is the angular acceleration of the wheel related to the linear acceleration of the blocks? We've talked about that in prior problems, but this is the example that we need to kind of focus on. In the past, I said, does the motion of one object correspond to the motion of another? I said that even today. If if the right box goes up a meter, does box 2 go down a meter? Right? That's how we started. In this case, if box 1 goes up a meter, do we get an equal amount of rotation out of the wheel? Now, that determines whether we can apply something that we talked about a while ago that vexed many of you. Do we have a reasonable relationship between the angular quantities and the linear properties of this system? Meaning, does one rotation of the wheel result in a circumference change in the motion of the objects? I think we can say yes. Because as this thing rolls, we are getting a direct relationship to the amount of string coming off of one side and the amount of string going on to the other. If so, then we have a way of relating the radius, the linear acceleration, and the angular acceleration. This is an exceptionally important caveat. You need to make it. Can we relate the angular quantities to the linear quantities? I believe in this problem, we can. I think it's very clear that we should be able to, which means that alpha is going to equal A over R. Right, the radius of the wheel. This has big implications to what happens next. Let's do the substitution. When I plug in A over R where alpha is, we get RTL minus RTR equals 5/3 MR squared A over R. Now, if you look carefully, all the R's cancel out. That was a point of contention for a person in sixth period. Look closely so I don't have to go back. I can cancel one of the R's now, right? That leaves one R in every term on both sides of my equation. I can factor it out on this side. And since it's non-zero, I can remove it. Now, I made a mess of it, and you should do your own freaking algebra and don't need me to do the algebra for you because, you're all capable algebra students. Saw it on your transcript. But that means I can write this as TL minus TR equals 5/3 MA. You do the math. Prove that to be true. But now I have three equations where if I add them together, all the tensions cancel. I have a positive tension here and a negative tension there. TL cancels. I have a positive tension here and a negative tension there. TR cancels. So when I add these three equations together, I get 2mg minus mg equals, let's go to the right side, 5/3 MA plus 2MA plus MA. Now, a quick bit of factoring shows me something important. The right side of this is still net force. Right? The two things that cause the system to move are the two boxes hung on either side of the wheel. So I have the weight of the one box on the left, the weight of the other box on the right, 2mg minus mg. In the parenthesis, I now have the total inertia of the system, including how the inertia of the wheel affects the system. Clearly more inertia. The inertia before was 3m. Now the inertia includes this 5/3 component. Now remember, the whole wheel has a mass of 3m, a point of contention we brought up many times today. But its contribution to the total inertia is only 5/3 m, much less, right? Around half. So that's quite a bit less inertia. Now, we should finish this. You should get an expression for the acceleration. And when you do, the acceleration is 3/14 g. Add those numbers together, cancel out the m's. 3/14 is clearly less than a third. This system will accelerate less due to the inertia of the wheel. Look, you need to